Okay, hello, this is the solutions for test 2. Question 1. In a hydrogen atom, an electron transitions from the n equals 1 energy level to the n equals 7 energy level. What is the difference in energy between both levels in electron volts? Okay, so let's find what each energy level is first. So I will first find the energy level of level 1 here. Which is given by this equation. The 1 squared on the bottom has been subbed in on the actual equation sheet that says n. And on the right, I am doing this for energy level 7. So I have subbed in a 7 for n. And going ahead and solving these, I get negative 13.6 electron volts for the ground state, the first energy level. And for this one over here, I'm going to save some, I'm going to keep a bunch of decimal places here. And this is also in electron volts. Now I'm looking for the difference. So delta E, so this is EF minus EI. So this is going to be E7 minus E1. Now we are told we are starting at the n equals 1 and going to n equals 7. So 7 is the final, 1 is the initial. That's why it's in this specific order. So the difference here was about 13.3 electron volts. I guess I'll plug this in. So I have about negative 0.278, I'll say, minus negative 13.6. So it ends up being positive 13.3 electron volts here. So in case you did not see why it's positive, this is why. It did matter. So our difference is positive 13 electron volts here. The reason it's positive is going to be important for part C. For part B here, though, find the wavelength. So this one, again, there are multiple ways to find the change in energy or the wavelength here, but I'm using two different methods that were most commonly chosen by you guys. So here's our formula for wavelength that I'm going to be using. Rearranging everything and plugging in all at once. This here is my constant for the capital letter R there. And my two fractions with n's already squared and a little bit simplified. This gives me about negative 93 times 10 to the negative 9 meters, or lambda equals 93 nanometers. Here. Oh. I forgot this. There we go. Negative. Okay, part C, is the photon being emitted or absorbed? Explain your reasoning. So there's essentially 3 different points here that should tip you off. First one is that the wavelength is negative. So the negative wavelength should immediately make you think, okay, did I do something wrong? Is there a reason this is negative? What's going on here? Second one is that the difference in energy level is positive, when so far we've only dealt with negative ones. And the third, well, I guess the first point you should have caught is that we are going from the first energy level to the seventh. So we are going up energy levels, which means the electron has absorbed energy, which means a photon has been absorbed. Absorbed because increasing n equals 1 to n equals 7 requires electron to gain energy from a photon being absorbed. There we go. So that was the first page here. Second page, number 2. A hydrogen atom is in its ground state. What is the angular momentum of the electron? So using our formula here, L equals NH over 2 pi. We are looking at the ground state, so N equals 1. So this just ends up being Planck's constant divided by 2 pi, which is actually just h bar, a constant that we had not introduced yet at the time of this test, but at the time of the posting of this video, we have covered. And you should know this as 1.055 times 10 to the negative 34 joule seconds. There are other equivalent units, such as the regular units for angular momentum that you may have remembered from a previous physics course. As long as the units were equivalent to joule seconds, I gave you the mark for that. So this one was basically just hey, when we actually learn about this, did you remember? Just a fun little thing for me, really. 3. Find the frequency of the longest wavelength photon that can ionize the hydrogen atom when it is in its ground state. Keyword here is ionize. That's the one that's going to tell you which formula to use, which is this one again. Same one as question 1. There we go. So we know that the photon will be able to ionize the hydrogen atom. This is going to be equivalent to the amount of energy that the electron has in its first energy level or in the ground state. So that is going to be equal to negative 13.6 times 1 over 1 squared. So it is still negative 13.6 electron volts worth of energy needed to ionize the hydrogen atom in its ground state. Great. So that was part 1. We are looking for the frequency of this photon. So we are going to set these two equations equal to each other and say that the energy of the photon is going to be negative 13.6 electron volts. Now, the only thing is we are going to change this negative to a positive because it doesn't really make sense for the photon to have negative energy. The negative is here because this is a potential energy. It's like a binding energy. It's the energy you need to overcome to ionize the atom. So the photon will have to have positive 13.6 electron volts of energy to overcome this. So when I switch this to positive in the next line, that is why. So first I'm going to rearrange this. I'm going to say F equals 13.6 over H. So I'm going to divide everything by Planck's constant. I'm also going to have to convert this because right now this is in electron volts. So I'm going to multiply by 1.602 times 10 to the negative 19 to convert this to joules. Because right now, Planck's constant is in joules seconds, so I need my energy to also be in joules for the units to work out here. So, plugging in everything, I get about negative 3.288, I'll round it off there, times 10 to the 15 hertz, so about 3.3. I don't know why I put a negative here. So there we go. Round it off. So 3.3 times 10 to the 15 hertz, or I think it's terahertz is the prefix. I don't remember the one for 15 off the top of my head. So that was questions 2 and 3. Question 4. So on the actual test, this one had a typo, so the correct answer was actually not there. This version in the video has been corrected. So the correct answer is one of these. It is C. There are other versions of the correct answer. So there are other correct answers that aren't listed here explicitly that are equivalent to C. I will write one of them down, but I'm going to show you how to solve for C here. So, starting with the equation listed here, I'm going to divide everything by mc squared. So I get EK equals EK over mc squared equals gamma minus 1. I'm going to add 1 to both sides, and I'm going to sub in for gamma at the same time. So this here is gamma, and that's going to be equal to EK over mc squared plus 1. Great. So I'm going to do, no, I'll do this one step at a time. I was going to combine 2 steps, but I'll do this one step at a time. First, I am going to make it so that gamma on the left-hand side flips, so that I get 1 minus v squared over c squared all square rooted, so that this is no longer the bottom of a fraction. And then everything on the right-hand side goes into the denominator as well. And now I'm going to square everything. One on top stays the same. Okay, there we go. Next, I am going to add v squared over c squared to both sides, and I'm going to subtract everything on the right-hand side over. So basically, all of this is being subtracted and moved over here, and all of this is being added and moved over here. Which sounds a little bit complicated at first, but it works out quite nicely. I'm just going to save myself some time and do this. There we go. Equals v squared over c squared. That's better. Okay, so they kind of just switch places there, which is nice. Now I'm going to multiply everything by c squared. And I'm deliberately writing it like this. So that when I square root to everything, the c out front gets square rooted, and then everything else is under the square root. There we go. That's a bit better. Great. So then this is our final answer. That matches C. Awesome. So there we go. And then lastly, an alternate version that is also acceptable. Oops. It's supposed to be 1 minus. There. So that was another alternate correct solution that someone else, that a couple of people ended up getting. So that was also accepted. If you called me over and did that one, I think everybody who did that one ended up calling me over, and I told them that they were good. So yeah, because there was a typo in the answer, this one ended up being just a bonus question on the test, but this is the intended solution. 5. An electron that is initially at rest is accelerated through a potential difference and reaches a de Broglie wavelength of 0.27 nanometers. How many volts must this potential difference be? 3 points. And then I give you a formula that could potentially be useful. This is essentially just the same calculation as done on the assignment, just a little bit easier. Instead of having you derive this formula that I've given to you, I just give it to you. So first, I'm going to find the momentum based off of the de Broglie wavelength. So that is Planck's constant divided by 0.27 nanometers. And I get about 2.45407 times 10 to the negative 24. That should be negative 24. That looks a bit better. Oh my gosh, I should just stop trying to draw extra lines. There we go. Great, and I'm going to take that and move that up over there a bit more. Great. So, here's my equation rewritten out. I'm going to be plugging in this number I just got and squaring it. Make sure you remember to square this number. When I was solving this, I forgot to square it and could not figure out why my answer was so far away from what I expected. For the longest time, it was embarrassing. Great. So, you should get about 3.305422371 times 10 to the negative 18, and this is in joules. Converting this to electron volts by dividing by E. So 1.602 times 10 to the negative 19. I get about 20.6 volts is the potential difference needed to accelerate an electron to be given a de Broglie wavelength of 0.27 nanometers. Great, so number 6 here, a photon has a wavelength of 100 picometers. and scatters off an electron at an angle of 45 degrees. What is the wavelength of the scattered photon? So my initial wavelength is 100 picometers, or 100 times 10 to the negative 12 meters. My phi is 45 degrees, and my final wavelength is a question mark. This is a Compton scattering question here. So I'm going to take my Compton scattering formula, and I'm going to write it down with a very slight rearrangement, where I just add the initial wavelength to both sides immediately. It's the only difference I made here. So writing all this out again, but with substituting in 45 degrees and plus 100 times 10 to the negative 12 picometers. Now lambda f is going to be equal to about 1 times 10. Well, I'll write it a couple more decimal places. 1.0071 times 10 to the negative 10 meters. So lambda f is about 0.1 nanometers. Or basically just identical. Moving on, question 7. This was a bit of a tougher question, but the actual calculation itself is probably the easiest. The actual math here is the easiest, but it's getting to that point where you can actually do the math, which is more difficult here. So when photons collide with an object, their momentum is transferred to the object they strike. When this happens with many photons, we call this a radiation pressure, where there is a force per unit area acting on an object due to the light shining on it. Using this theory, we can construct a solar sail to propel a spacecraft through the solar system using wind. This should say using light. Using light. Very similarly to how a ship sails using wind. I can't believe I never caught that typo. Why didn't anybody tell me about this? Did nobody read that part of the question? No one told me. Oh no, I feel like an idiot now. Okay, number 7. Find the radiation pressure acting on the solar sail of a spacecraft. Some things to remember. The solar intensity just outside of the Earth's atmosphere is 1,370 watts per meter squared. You might remember that number being an even 1,000 on the assignment. That is not a mistake. The 1,000 is at the surface of Earth. This 1370 number is outside of Earth's atmosphere. So Earth's atmosphere absorbs some of the solar radiation, some of the light from the sun. So naturally it will be stronger outside of the atmosphere. So that's why this number is larger by a surprising amount. Well, maybe not surprising, but at least significant. Next thing to remember, total photon momentum is equal to the total energy divided by the speed of light. I give you the equation there. And then pressure is equal to force divided by cross-sectional area. So again, I give you the equation here. Some other equations from the formula sheet that will be useful are that force is equal to momentum divided by the change in time. So force is equal to momentum divided by time, and this is not the same P. So I'll say momentum there. And lastly, we are going to need, where did I put it? The bottom equation here in the bottom right. E equals that where the energy of light from intensity of the light is equal to, the intensity of the light multiplied by area multiplied by time. So E equals A T. Okay, great. So the only number we're given is intensity. We do also know the speed of light as well. So those are the only two numbers we actually have. So let's figure out how to find the radiation pressure acting on the solar sail of the spacecraft. So I know I am looking for pressure. And I know that pressure is equal to force divided by area. Great. Where to go from here? Well, I don't know the area. I'm not told what the shape of this solar sail of a spacecraft is, so I can't say anything about the area, at least not right now. So let's leave that alone. However, I do know that force is equal to momentum over time. So I can say that radiation pressure is equal to momentum over area, cross-sectional area times time. Great. Same thing. I don't know how long the time takes. I still don't know anything about the area. So I'll leave that there. But what I do know is that momentum is equal to the energy divided by the speed of light c. So we're simplifying this a little. I have that the radiation pressure is equal to energy divided by cat. And I know that energy is equal to IAT. Great. So now I have time and area on the top and bottom, so they cancel out. So radiation pressure is only dependent on the intensity of the light. So I'm going to plug in 1370 and the speed of light c, and I get about 4.566 micro newtons per meter squared. For the units, you could have given me anything equivalent to newtons per meter squared. I'm using newtons per meter squared because of this definition here of pressure. Here we have units of newtons over units of area, which is meters squared. So newtons per meter squared is the unit of pressure here. So that is my answer. And just for completeness, 4.566 times 10 to the negative 6 newtons per meter squared. There we go. Just to show that the micro, the mu there, the Greek letter mu, is, well, what it is. Just for completeness. So that was number 7. So that was the end of the calculation questions. On to the lab concept questions now. Number 8. In the polarization lab, where we used 2 polarizing filters and measured the intensity of light, we used our regular helium neon laser as a source. In the datasheet for the laser, it is stated that it has a random polarization. Explain why this random polarization did not significantly impact our results. It did not. And it has a random polarization. The key here is that we had 2 polarizing filters. The first filter was untouched. Leaving us a constant linearly polarized of light incident on the second filter. Great. So yeah, just the first filter, passing the light through the first filter and not touching the first filter at all, left us just a constantly polarized beam of light hitting the second one. Great. Number 9, in our Brewster angle lab, we reflected light off a microscope slide to find the angle at which there was minimum intensity. Some of the light was reflected off the front surface of the slide, and some of the light passed into the glass slide and then reflected off the back surface of the slide. How could this have impacted your measurement of Brewster's angle? So what this is talking about is that some of the light, and actually, I'm going to do this. Some of the light would bounce off the front, and some of the light would bounce off the back. Now, in Brewster's angle calculations, the order of what material you're going through matters. So this is air, this is glass, and this is air. So at this first interface, the first reflection off the front surface, so front, back, the reflection off the front surface is air to glass. Front, air to glass. And back is glass to air. Right? So if we call these N1 and these N2, when we look at our Brewster angle formula, which actually I think was on that previous page. There we go, down here. I'm gonna just copy this. There we go. So when we look at this, the different reflection points on the front and the back will have different Brewster angles. So for the front, we are going to have about 1.5 over 1. And for the back, we're going to have about 1 over 1.5. So very clearly, these are going to be different angles, which means that because the Brewster angle will be different for both surfaces. It may make it more difficult to find the point of true minimum intensity. So there we go. Basically, if these two beams of light being reflected off the front and the back surface are close enough together, it's going to make it much harder to determine where the actual minimum is. If they are, for all intents and purposes, for our eyeballs, just eyeballing it, which is literally what we did, if they are too close together, we won't really be able to tell the difference between the front and the back just with our eyes. So the point at which it seems to be minimum intensity for us will be that will actually be the overall minimum intensity of both of them together, and not just the minimum intensity of that front surface or of the back surface there. It did not matter if you used the front or the back surface. in the lab, we assumed we were looking at the front surface. You can still do the calculation either way. Doesn't matter. So those were questions 8 and 9. And our last couple of questions for the test here, starting with number 10. In our spectroscopy lab, we observed that the spectral lines of mercury, hydrogen, and neon, some of these lines were actually two lines that were very close together. Think of the like yellowy, orangey lines on mercury. They were very, very close together. They are a good example of that. Using your knowledge of energy levels and electron transitions between them, explain why some lines are very close together. Very close together. I don't know why that says each other there. I'm going to fix that. Very close together. And why some are farther apart. Great. So what I'm really looking for here is why some of these lines are so close together. So if we have energy level here, and another one here, another one here, and here, and I'll put the last one down here. If these are energy levels, and we have an electron on this one, and an electron on this one, and they both jump all the way down to here. There we go. This total jump is very, very, very similar. They have near identical jumps. The change in energy is super, super small between their starting points, and the overall jump distance is basically identical here. So for two lines to be close together, two electrons must start at close and high energy levels and jump down to the same energy level. For far apart, it is anything else, really. So if you have an electron here and an electron here, and one of them jumps here and one of them jumps here, those jumps are very clearly very different sizes, so very different photons will be coming off, and they will be far apart. Okay, so 11. In astronomy, spectroscopy is frequently used to analyze stars and planets. Explain how an astronomer could determine what atoms a star is made of by analyzing the full spectrum of light it emits. Assume this star creates all wavelengths of light in its core. So what we're going to have here is a full spectrum of light. This is going to be the opposite of what we have seen in our labs. So in our labs, we saw a black, 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 black. We saw nothing, and then a single line of like an indigo for mercury. And then nothing, 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 just black. And then we saw a line of green. And then nothing, nothing, nothing. Then we saw two lines of yellow. And then nothing. So we only saw specific bars of color there. Now, in a star, we're going to have some red, some orange. There will be some yellow in there. Some green. Some blue. And some purple. However, if this star contains, let's keep using Mercury as an example, we're going to have a violet line that's missing, a green one, and two yellow ones that are close together. They're going to be missing. you're not going to have any wavelengths there, because the Mercury in the star would be absorbing that light instead. So the light is made in the core of the star. The light then has to pass through everything that the star is made of before it escapes the star, and the wavelengths that correspond to the elements that make up the star will be absorbed. Everything else will be passed through. So by looking at what wavelengths are missing from the spectrum, we can determine what elements are in the star that are absorbing those missing photons. So all these spectra that we have been looking at so far, they are both absorption and emission spectra. So that was the key to this one here. The bonus in the following equation, why is the energy always negative? It is potential energy. It is defined as being, because it's potential energy, it is defined as being zero at infinite distance. It's a potential energy between the electron and the proton. So if you move them infinitely far away, then there's no more potential energy between them. It becomes zero there. If you want a slightly more in-depth explanation, because this one's just really quick, please take a look at, I think it's around slide 22 on week 9's lecture notes. So please go take a look there for a slightly more in-depth explanation. So that was test 2. If you have any questions, please email me or see me in person. Thank you.